All right, you should be able to see that. Okay, so my module is in some ways a little different from some of the other ones in that it's not designed so much for a course. It's more designed for self as a self-directed course. So if you are a student, or if you have a student who you think might want to use these tools, you can point them at this and they can go away and learn how to use and apply the methods. So I want to talk today about the HydroLearn module. I also want to talk about the MESAs package that sort of sits underneath and is now available on Conda and GitHub. I'll just mention that briefly at the end. So first of all, for the uninitiated, what is storage selection? It's a generalization of the idea of a transit time distribution and related concepts to time variable systems. So it's useful in, particularly in, for instance, in understanding the transit time distribution through watersheds. It's useful for analyzing tracer data, particularly stable water isotopes in watersheds and active stream tracer injections when you're looking at transient storage or hyperrhea exchange in rivers. And it can provide a basis for forward modeling of time variable non-ideal mixing. I just wanted to sort of start off with this little video. I won't show the whole thing, but as part of this course, I put together a lot of visualizations and videos to help students understand. So this is just a little introduction.
What is a storage selection function?
Yeah.
Okay, so there's an analogy that can help us understand. It's the transport column analogy. Imagine this is all the stuff, usually water, in a control volume. We use age-ranked storage to arrange the stuff in terms of the order it arrived, with the youngest at the top and the oldest at the bottom. New stuff arrives at the top of the column, like so. But outflow leaves via imaginary offtake valves arranged along its length, like this. The outflow rate might vary along the length of the column. So for example, you might have lots of young water coming out the top and not much old water coming out the bottom. Let's draw a curve plotting the relative outflow rate as a function of age-ranked storage, like this. Now, normalize the values so this area is equal to 1, and this is the storage selection function, at least the density form. Again, this is just an analogy. What is a storage selection?
All right. So that was lots of fun putting together those, and all those illustrations were done on my iPad. How do I get to the next slide? So the HydroLearn module is a gentle introduction. It's a self-directed course designed for people who have data sets and are okay with a little bit of Python coding. Most of what's in here is just copy and paste, so you can follow along. And it's really designed for people who prefer visual explanations and hands-on learning over all the math and derivations, which, as you can see in the contents, is really relegated to the end of the module, the more math-heavy stuff. At the start of the course, there's 41 learning objectives listed in great detail, but they can be sort of summarized like this, that the emphasis is on understanding the underlying concepts, applying them using synthetic and real data sets, analyzing the results to try to gain real insights into systems, and evaluating different options for further analysis. Throughout the course, I've put together a lot of visual explanations, built on this idea of the transport column as a way of breaking up the text and hopefully making some of the concepts much easier to understand. Throughout, there are, or will be, not quite yet, but there will be frequent check your understanding quizzes. So at the end of each page, there'll be a series of true and false statements, and you have to choose which ones are true and false, and I try to make it as tricky as possible so that you can have to really understand the content to be able to pass the quizzes. I'm trying to emphasize in the content practical applications to real data sets and trying to think about, what are the issues that you'll come across when really applying these ideas, and how do you gain insight into a real system from this analysis. The capstone learning activity is an analysis of a stream tracer breakthrough curve dataset supplied by Adam Ward, who's going to be speaking next. And in future additional material, I intend to keep expanding this course. And future additional material will include an example application to a watershed, which is more complex. So I want to be able to introduce a few more ideas before I go into that. There's frequent code examples throughout the course. So there's lots of these little copy and paste code snippets that you can, and explanations for how they work. And with the code that is supplied, there's custom visualization tools that I've put together to help you interpret your results and connect those results to ideas from the course, like this transport column concept. You can actually plot the transport column and what it looks like for your system. And there's an example of sort of what the actual visualization looks like in a Jupyter notebook. There's step-by-step instructions for creating simple examples, for setting them up, running them, and visualizing the results. And all of the code examples can be run on Quasi Jupyter Hub or on your own computer. So everything can be installed either on the Jupyter Hub on Quasi servers or on whatever server you have access to. Okay, so let's have a quick look at what this actually looks like. So I'm now going to share a different window. Yeah. Okay, so this is the course outline. It starts off with a bit of information about how to get started with Mesas.py, including that step-by-step installation and creating first example. Then there's a background section to just make sure that you have some of the fundamental concepts around material balances, mass balance, and also things like age and transit time and residence time distributions. The main content, I guess, is in section 2 then, the fundamentals of storage selection, which sort of goes through and alternates between more sort of concept heavy parts and then applications of those two data sets to using code. And then it has a capstone learning activity, which is the stream tracer experiment. And then the last section sort of is more mathematical, giving the derivations of the underlying equations. I just wanted to show here sort of these overall learning objectives listed at the start, which I won't read. Here, for various reasons, I can't show you, unfortunately, all the underlying module units here, but I can show you what it looks like in the back end. And so you can see each one of the units has a prefix that tells you whether this is a section that's going to try to teach you some conceptual tools, or is it something that is going to teach you how to code and use the Mesas.py code, or is it an activity where you'll get step-by-step instructions and you can try to understand what's going on. Here's an example of a concept unit where each concept is associated with visualizations and visual metaphors to try to illustrate the concepts. The coding sections sort of try to give you lots of examples of how the code works and what it does along the way. And then the activities involve, basically copying and pasting the sections of code and showing you what the output that you get ought to look like. So you can make sure you've got the right, you've got it all right. The capstone learning activity, which is the piece that's done with Adam Ward's data based on a stream tracer experiment. Looks like this, and I'm just going to step through so you can see how much detail there is in helping you to apply what you know. So going from getting the data from HydroShare, setting up the model, wrangling the data to make sure that it's in a format that the code can use, accounting for unrecovered traces and other sort of methodological details, setting up and running the model, visualizing the output, evaluating goodness of fit, fitting a distribution, and then a final set of analysis tasks and questions that you can set yourself to do and then to think about. And if you wanted to use this course in a real graded course, these might be the basis of an assignment that you could give to students. I'm not looking at the chat window, so I don't know how much time I have left. Plenty of time, it seems. I just want to show you what the Jupyter Hub looks like. So this is the quasi one, and my session's timed out, so I can't show you that. But fortunately, I've got it set up on my own computer. So this is sort of an example of what, you know, if you copy and paste all the pieces, it will give you outputs that look like this, and you can see what that real kind of time series and transport column examples look like. This is what the capstone example looks like, where you read in data sets. You can actually see all the time series of data there. Here's the observed inputs and outputs. Here's where we're trying to fit a breakthrough curve in a simple way, and then I scroll down to where the end of the optimization is. This is our final fitted storage selection function, and the observed and predicted basically lying on top of each other. And so we can estimate things like the volume of storage in the reach from that. Okay, so then the last things I wanted to show were just that the MESA's code that's underlying all this is available on Anaconda Cloud as a Conda package. And if you want to install it on your own computer, you just basically have to type that command in, and it will download all the dependencies and install itself. So that I went through that quite quickly, but I'm happy to take any questions. The enthusiastic voice actor Adam was my identical twin. Much better looking than me.
All right, so we have about 7 minutes left. Any questions for Kieran about his module?
What app did I use to make the video? So the video was made, the actual drawings were made using Procreate, which is an app on iPad. And then in Procreate, you can create basically a GIF or a video file, an MP4 file of cycles through a series of images. And once I had that, I used, I forget what the program is, but I used a different program to record my voice and put it over the slides. More questions? Open Broadcast Studio, another option. Haven't tried that. Can I create a HydroLearn module on how to create videos? I will defer on that one and leave it to the experts. I just Google things and muddle through.
Hi, Kieran, this is Belize. I have a question for you. This is fantastic. Really great to see it coming together. Can you talk more about, do you have kind of an authentic learning experience? That's what I'm assuming is sort of within this capstone, but is that more about taking your own data and just taking a look at it? Or do you talk through an example of, you know, why someone could care and how they're going to use the results from what comes out of this?
So the sort of the authentic learning activity is the application to the stream tracer data. So this is where you're trying to understand how big is this stream, how much there's so much that you can see on the surface, but using a tracer you can sort of try to understand what's the volume that the stream is actually exploring in the hypereic zone and in the transient storage around the channel. There's lots of reasons why that's important and interesting. I could probably do a little bit more to motivate that at the start. I might look to Adam to help me come up with some good language for that. But the idea is it is an authentic learning activity in the sense that it's real application to real data, and it walks you through how to do that. I guess it's the kind of thing where it's really geared towards like a researcher or a student or a field scientist who wanted to who has a data set and they want to analyze it using these methods.